interference and modulation. So we are now, up to now we've restricted ourselves to a single frequency. We've just thought about omega as the frequency, right? But at the beginning I showed you that there's a whole range of frequencies. So when it really gets interesting is when you look at the relationship between different frequencies in a wave phenomenon, right? That's when you start to get things like modulation, interference, dispersion, right? Dispersion is our target today. So now let's just think about two frequencies. Imagine we have two frequencies, or two wavelengths. You have, well, let's stick to frequencies. So you've got the blue wave, yeah, and the red wave. And unfortunately, they've decided to, on this diagram that the blue one should be a lower frequency. I don't agree with that, but if it's blue, it should be high frequency, right? And red. But anyway, the blue wave is slightly longer here, and the red wave a bit shorter. And so you can see the result of that is, if you start from a position where they're in phase, the red wave oscillates a little bit quicker, the blue wave a bit longer, and so they go out of phase. And so where they're reinforcing here, they are cancelling each other out perfectly here. And then they come back into phase a bit later on, and they're reinforcing one another again, okay? So if you look at the amplitude, if you plot the amplitude, it's double here, and it's 0 here. And what you get is this packet. So you get something which oscillates with pretty much the same frequency, but there is a modulation of the amplitude. And so it's got a large amplitude, small, large, small. And this forms wave groups, or groups of modulation, right? That's how AM radio works. You remember radio, right? In the old days, we used to have radios where you could tune into a radio station, and there was AM and FM. Now, AM stands for amplitude modulation, which is what we're talking about here. FM is frequency modulation. So, history lesson for you. So, are there any guitar players in the room? Anyone play guitar? Yeah. So you know how to tune a guitar, right? You get two strings. You've got 6 strings in it, and you do them in pairs, right? So if you put 2 strings together, and you pluck a string, and you put your finger on the 5th fret and pluck the next one, and they should sound the same, with one exception halfway down the fretboard. But basically, you put your finger on the fretboard, so the frequency should be the same of the 2 strings. You pluck them together, right? And it goes woo 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 woo. It sounds horrible, right? So you think, oh no, that's not right. So you turn a bit, and then it goes woo 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 woo. And you turn a bit more, it goes woo, nearly there, just a little bit more, and then woo. Perfect, okay? Go to the next pair. And that's how you tune a guitar. And at the end, you pluck your bottom E string and your top E string, and they don't sound like they're 2 octaves apart, so you think, oh shit, this guitar is rubbish, I have to buy a new one. All right? So anyway, what's happening there is that what you're listening to, that woo, 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 that's called the beat frequency. And it's the frequency of this packet, this modulation packet. And as these things come to the same frequency, the modulation disappears. Right? The frequency of the beat is just the difference between the 2 frequencies. So how this applies to waves is that now we think about these waves as propagating. Right? So the red wave, the blue wave, they're both propagating in the x direction in a fairly similar way because they're very similar to one another. They've got similar frequencies, similar wavelengths. What about the packet? How is that propagating? Is it propagating the same way? Or is it propagating at the same speed? Not necessarily. It could be propagating at a different speed. It could even be going the opposite direction. Right? Sometimes you see that in traffic, okay? There's a jam on the motorway, and you come to a sudden stop. You've got to leave a reasonable distance in front of you, right? And you hope that you don't have a BMW behind you, right? And so it comes to a stop, and then it gets going again. It comes to a stop, gets going again. These are compression waves in the traffic, and sometimes they go the opposite way to the traffic, which is why you have to be very careful. in traffic. Anyway, these are groups, and they can propagate as well. So how do they propagate? Well, here's an example, and this example is from deep water waves. All right? So here's a wave packet propagating, and in this case it's propagating in the same direction as the individual crests and troughs. So if we mark an individual crest here and follow it as it propagates through this packet and out the other side. And at the same time, if we mark the middle of the packet with the circle and see how that propagates, you can see that they're not propagating at the same speed. The individual crests are going faster than the packet. Yes? So the individual crest, that's called phase propagation, and the packet, that's called group propagation. And this is how deep water waves behave. In fact, for deep water waves, and we'll show that later, the group speed is half of the phase speed. Okay. So think of it as a packet moving along, and individual crests are propagating through the packet, amplifying, and then going out the front and dying away. Right? And what's interesting about this is that the energy associated with this perturbation propagates at the group speed, and the information propagates at the group speed. So we're talking about phase propagation, group propagation, and the speed at which a packet, a modulation packet, will propagate. Let's analyze that a little bit. So let's write down the description of two waves which are very similar. They have very similar wave numbers, K1 and K2, and very similar frequencies, omega 1 and omega 2. Right? So for the first wave, K is K plus delta K, omega is omega plus delta omega, where the deltas are very small. Right? And for the other wave, K2 is K minus delta K, omega 2 is omega minus delta omega. So there's these small differences between the two of 2 delta K and 2 delta omega. And so let's just write down the wave function for the sum of those two waves. So that would be the real part of an amplitude, assuming they have the same amplitude, times e to the I k1x minus omega 1t, plus e to the I k2x minus omega 2t. Right? So that can be written as, if you substitute these relations here into these k1s and omega 1s, k2, omega 2, you can write it down like this. It's e to the I kx minus omega t, so that's our original wave, times this thing, which is e to the I, something to do with delta k and delta omega, and same thing again. Right? So with minus I. Right? So that is actually the cosine of delta kx minus delta omega t. So what we have then at the end is, well, 2 times the original wave multiplied by the cosine of another wave. But this other wave, instead of k, it's got delta k. And instead of omega, it's got delta omega. Now, this delta k is small, right? So what does that mean? The effective wave number for this modulating function is small, which means that the effective wavelength of that modulating function is long. Right? The effective frequency for that modulating function is small, which means it has a long period. Okay? So what we have then is the original wave times 2, modulated by this thing, which has a very long wavelength and a very low frequency. That is the modulating packet. Okay? So we've reconstructed, we have a wave, and this amplitude is modulated by another thing, which is also propagating, right? Because this is just the same description as this. It's a cosine function, kx minus omega t. It's just describing a longer wave with a lower frequency. So this this modulating packet, we can work out its speed as well, its effective phase speed of the modulating packet. And that will be omega over k as before, except it's delta omega over delta k. So the speed of this modulating packet is delta omega over delta k. And if we take the limit that delta becomes very small, we can actually express that as a function. It's d omega by dk. Right? So that is the group speed, and it's a general property of waves in which there is some sort of relationship between the frequency and the wave number. Right? If you know that relationship, you can differentiate omega with respect to the wave number, and you can calculate the group speed. Right? So that becomes a powerful general thing. We started off just talking about two frequencies, two discrete different frequencies. Now we have a continuum. We have a relationship between frequency and wave number. And we can use that relationship, well, to start with, we can work out the phase speed, omega over k, which is a function of omega and k, obviously. Right? So different frequencies might have different speeds, right? And that's just the phase speeds. Now, also, d omega by dk, that's the group speed. That's the speed at which a packet will displace. And that also we can work out if we know the relationship between omega and k. And that also might be different for different frequencies. Right? And so we have two things here, both of which are a function of wave number and frequency. The phase speed and the group speed. And what we need is a relationship between the frequency and the wavelength, between the frequency and the wave number. That is the key thing. Right? And if we know that, we can work out the speed at which an individual crest will propagate, that's the phase speed, or the speed at which the information or the energy will propagate, that's the group speed. This relationship is called the dispersion relation. Right? The relationship between omega and k, or between omega and L and M, depends on the physical problem we're looking at. But that relationship is the key, and that's called the dispersion relation. We're going to spend the rest of the course looking for dispersion relations. Okay? That's what it's all about.